Hello everyone and welcome to this lecture. I apologize for not being able to be there today due to a family emergency, but I sent this video which will cover the same material. So when last we met, we were developing visualizations of these different configurations of reactor types and estimating residence time distributions. And we introduced this problem. We said, let's say we have a stream that enters a plug flow reactor, and at the exit from the stream, part of it exits the system as simply as we expect. Then part of the stream splits down this way, enters another PFR, and rejoins the original stream. Right, so once more, we have a stream that enters the primary PFR up here, and then at the exit from this PFR, we have a stream that exits the system and a side stream which splits down to a second PFR, and that exit rejoins the first stream. So there's basically a recycle through a PFR. So we want to determine the RTD in this situation. And the best way to do this is through a kind of thought experiment. So we can imagine injecting a pulse of tracer to the inlet here. And remember, we are only dealing with this inlet and this output, because in principle we have some real reactor somewhere, and there's some kind of complex mixing pattern going on in here, and it might be that this system that's been proposed is the equivalent or is a model for the kind of mixing going on in here. And so in this real reactor, we can only take samples or make injections here and here. So we are injecting with some tracer here, and we are taking a measure out here. The rest of this is considered to be part of the model that describes the actual mixing going on in here. So when we do the thought experiment, we are allowed to imagine a pulse input here, and let's see what happens to this pulse as it passes through the system. Right, so remember, in our experiment we would be measuring tracer at the exit here, and we'd get some signal out, and that would be concentration in time. And of course we have E, the exit age distribution is the concentration divided by its own integral. Right, we derived that relationship. So any signal that appears out here is going to be proportional to C, right? That's going to work out to some constant. So the exit age distribution is proportional simply to the concentration appearing at the exit. So let's see what kind of concentration we get here. So we assume that we are creating this pulse at time 0. So let's sketch out what we would get. So E as a function of, instead of time, I'm going to use age, right? So let's label the space-time in this plug flow part as tau P1, and this would be tau P2. So we can imagine we've put in this pulse here. It reaches this PFR, and of course we assume that this line is small enough that it offers a zero space-time. So so pipelines are considered zero space-time zones. So here, after a period tau P1, we will have a contribution from here. So when we reach tau P1, we'll start seeing some tracer at the exit. Right, and of course we've got 0 before that. So up to time tau P1, nothing will appear from this pulse. So only after tau P1 time units pass will some of this pulse start to appear here. And of course we don't get out everything possible here, right? That pulse is going to be split up at this point, right? The whole pulse is traveling here, the whole pulse passes through here, and then it reaches here, and part of the pulse goes down here and part of the pulse goes up there. So the pulse going down here is going to enter this PFR and is going to be delayed by tau P2. Then it goes up here, and remember, we aren't pulsing anymore, right? After time 0, right after 0 here, we don't inject any more tracer. There's no more pulse going to the system. So now tau P1 has passed. We've seen some of that at the exit. and then sometime later it passes through the second, the amount that's split off passes through here, goes up here, and then it will be delayed by tau p1. So after tau p1 plus tau p2, we will get another contribution at the exit. And of course, this contribution will be less than it was originally. So originally we have a certain amount coming, exiting here, and then some fraction of that is going down here, and then appearing out here. And when that fraction exits here, again, part of that will go down this way. So we'll get here at, and remember this distance here is tau p1 plus tau p2. So this point is at 2 tau p1 plus tau p2. Right, and then after we get the contribution there, the amount that splits down here is again going to be delayed by tau p2 and then tau p1. So after the same interval, we will get yet another contribution. So, and that's of course at 3 tau p1 plus 2 tau p2. Okay. And so each time we get a contribution at the exit, there is a certain fraction that exits down this way and recycles around and up here. So at each stage we are losing some of that tracer. So this is going down, and so we keep getting that, right? These are empty points and there's one solid point there, and we have zeros in between. Right, so we keep getting this progressive decay, but it's a kind of interrupted exponential decay. And if you think of it, you could view this circulating pattern as a kind of CSTR, but it's a kind of interrupted CSTR. It's got these plug flow delays in between. So that's why we get this CSTR exponential die-off type of thing, but with these peaks in between. So that explains this this weird shape for our exit RTD in the case of this recycling plug flow reactor case. Okay, so that was the one you were to think about as homework over the long vacation, and we want to now go back to kind of the simpler cases. Well, this was the kind of interesting one that was going to keep you up at night. Let's go on to some of the not less interesting ones, but well, you know, these ones without as much complexity. So let's say instead of recycling, we simply had two PFRs in parallel. Right, so we have some real reactor, and then this is our model of what's going on in that reactor, that there are two zones, and they have generally different space-times. So what do you think that's going to look like? What's the exit RTD there? So you can pause this now and try it out, sketch out what you think we'd get for E and I, and when we come back we'll look at that solution. Okay, let's have a look. So let's sketch first E of theta. So again, if we apply a kind of thought experiment, imagine a pulse here, and of course we've got some real flow rate Q, and let's say we've got equal flows in each direction. So we've got Q over 2 here and Q over 2 there, but these volumes are different. So as I've drawn it, perhaps this is a bigger plug flow than this one. So this is going to have a larger residence time than this one. So tau p1 is greater than tau p2, and so we would expect to get a pulse, the pulse being delayed by tau p1 here, and then the same pulse will be delayed by tau p2 down here. So we would get a contribution here, tau p1, and another one down here, tau p2, right? And of course for the internal RTD, we would anticipate that in the system we would get all the material retained up to tau p2, right? The earliest time anything can exit from the system is tau p2. So internally we retain all material until tau p2, and then after tau p2 we are only retaining material from the first tank. So this will extend further until, well, let's try and draw these in line, right? So until tau p2, sorry, tau p1. And so that's the latest time that you can spend in that system. So after tau p1, everything has exited the system, and so it's on a 0 thereafter. So this is the internal RTDI of theta. Okay, so that's PFRs in parallel. Now let's think of CSTRs in parallel. So we've got two CSTRs. And again, we'll apply tau p1 and tau p2, or rather, in this case, we'll call it tau s for stirred tank, tau s1 and tau s2, which are generally different. And again, we can assume perhaps the flow rates are equal, but this volume is greater than this volume. So this space-time is greater than this space-time. So if we have these two in parallel, then we can imagine that we will simply get two exponential decays. So if we pulse some tracer in here, then we can imagine if we could somehow measure at this point, we would get an exponential decay here, and then similarly we'd get a different exponential decay here. And I'm deliberately drawing them with different extents of decay, or different rates of decay, because we said this had the greater residence time. So if it's a greater residence time, it starts lower. Remember, it's E of theta for the CSTR is 1 over tau e to the minus theta over tau. So if tau is greater here, then 1 over tau is smaller, so you start lower, and then 1 over tau again is smaller, so it takes a longer time for this to settle out, and then the contribution from this one being smaller is sharper with a faster drop-off. Right, so in essence you get the superposition of two exponential decays. And of course, since we can only measure at the exit point, right, we can't measure individually here. Like we said, this is some model of some real system, and we don't know where in there to go and perhaps do a sample or something like that. So what we would really observe is the sum of these two. So we might see something like that, right? And so it depends how sharp this is, how different these space-times are. If the spacetimes are closer together, then when you do this experimentally, you might not be able to discern this this kind of difference in gradient, because it's a continuous curve, and it's the sum of two exponentials. An exponential function can fit this fairly well, but anyway, it actually is the sum of two exponential functions, and so it's not a pure exponential anymore. So that's what we get in the case of CSTRs in parallel. Another one to think about is in series, right? So let's look at PFR in series with another PFR. And again, this is a model of some real reactor. So we've got some real reactor here, and its mixing pattern might be such that this is a decent representation. So sketch out for yourselves the internal and exit RTDs. Maybe take a minute and let's and try to estimate what your RTDs look like. Okay, I'm assuming you are unpausing and you've tried this now. So for a PFR, actually this is going to function as just one long PFR. So your tau, if we just label it tau P1 and tau P2, what's really observable is the sum of these two. So in effect, you just get the same RTD as for a single PFR. So you get a single exit peak at tau P1 plus tau P2. In other words, if you introduce a pulse here, it's going to be delayed by tau P1, and then you'll get a pulse coming out here. And then that pulse will also be delayed by a further tau P2. So that's what E of theta is going to look like. And then, of course, I of theta is in a similar way going to, everything will be retained up to the time tau P1 plus tau P2, and it's 0 thereafter. So empty, well, that's a matter of choice there. But anyway, that's the case of PFRs in series. Then, of course, how about CSTRs in series? So if we have CSTR here and here, then again with the thought experiment, if we introduce a pulse here, we know that after CSTR, the influence is to exponentially decay that pulse. So we'll get an exponential decay exiting here. Then for the second tank, that exponential decay is going to be further decayed, and it turns out it decays it in that way. So let's figure out why that might be. Let's put some labels on first. So of course, if it's in series and if we are at steady state, then the volumetric flow rate will be Q, Q, Q. And then these volumes don't have to be the same, right? In principle, you can have different volumes for CSTRs in series, but let's just say they are. Let's just say we've got V here and V there, right? So there exists tau, which is not the same as our overall tau, right? If this is a model of a real reactor, and let's imagine the situation when this can actually arise, right? This kind of situation. Let's imagine that we have two mixers in some long, shallow vessel like that. Then we can imagine two well-mixed zones in that reactor. So you can actually get, you can approximate this kind of behavior in the real world, right? So if we have this kind of situation, we can imagine that there exists a certain real volume, which we'll call V naught, and then there's a real flow rate Q naught. And in principle, the flow rate between these two zones must be Q naught as well at steady state. Right, so there exists a space-time tau naught, the real space-time, but in these, in our model case, we can identify this kind of, well, this is still Q naught, right? But this V is V naught over 2, right? If these are equal volumes, then it's half the total volume, V naught. So let's develop the model here, and of course for the pulse case we can say ddt of C is So there's a pulse here, but there's no pulse after t0. So writing this balance only after t0, there's no contribution from this line, and then we have a constant loss here. So this is minus CQ. And then we have to multiply by volume here, of course. So we can write this as ddt of C is minus C over tau, where tau is V over Q naught. Right, so this applies to the first tank. So let's say this is the concentration from number 1. And now let's do the equivalent thing for number 2. So if we write this balance on tank 2, we write ddt Vc2 equals, and in this case, after t0, we can't say that the inlet is 0 anymore, right? The influence of this first tank is to exponentially decay the signal. So even after t0, we have a non-zero tracer contribution here. So we can rewrite this as QC1, and then we do have an exit stream from here, so this is going to be QC2. So we can write ddt of C2 is C1 over tau minus C2 over tau. But C1 is a known, we have a solution to C1, right? This is a simple homogeneous first order ODE, which has the solution C1 is C1 initial exp of minus T over tau, and if we let theta be T, it's theta over tau. And so, or rather, let's leave the T in because we're going to use that here. So using T here, then we can write ddt of C2 is equal to C10 exp of minus T over tau minus C2 over tau. Right, and if you look at this equation, the variable of the equation is C2, so we do have a C2 in here, and then this is an explicit time dependence. So this is a non-homogeneous ODE, and we can use the method of the integrating factor to solve this equation. So let's have a look at that solution. Okay, so this is what's in your class notes, and you can see here that's the balance on the first tank, and here I'm using H instead of a V, right? So C1, there's a Q, so that's all the same. Here I am using theta instead of T, but that's fine. So that's the concentration from the first tank. And then in terms of the second tank, it's the same balance as we've just seen. So we should use V here instead of H, and then this is the flow coming in from the first tank going into the second tank, and then that's the flow coming out of the second tank. And then if you just put that in the standard form for the integrating factor method, you can write it like that. And so this is the point that we left it at when we were writing it up just now. And then you can show that it has the solution, right? Just look up the integrating factor method. So you've got an explicit dependence on your variable. In fact, I should be using t instead of theta here because then you can see the explicit time dependence. But anyway, yeah, so if you write it in terms of theta instead of t, then you've got that for C2. And then you can do a similar thing for 3 tanks in series. And then for 3 tanks in series, of course, you would write your balance would look like this. You would have ddt C3 is C2 over tau minus C3 over tau. Right? You can see that's a similar form to what we got for the second tank. So if you have 3 tanks in series rather than 2, so say we had a third tank here, then we would say the rate at which tracer entered here would be C2 times Q, and the rate at which we exit here is C3 times Q. So we can write a similar balance here, and then C2, we have this explicit function here, so we would end up with the same setup, dC3 dt plus C3 over tau equals, and then now instead of C naught e to the minus theta over tau, we would have C naught theta e over tau. And so the solution to that looks like this. So for 3 tanks in series, that's the solution you get. Okay, and so if you then work out E of theta, right? So far we've been working in terms of concentrations. If instead you use this relationship which we mentioned here, right? If you work out E of theta simply by integrating under the curve, then you would get that form. And you can do this any number of times, right? 2, 3 we've talked about. You can go 4, 5, as many times as you like. And for n tanks in series, you can show that this is the general form, because you can see the progression here. When it's 1 tank, we have just C naught e to the minus theta over tau. When you have 2 tanks, you also have C naught e to the minus theta over tau, and you have that extra theta in there. Then for 3 tanks, you have the same thing, and then tau squared, and so on. So when you have n tanks, it's theta to the n minus 1 e to the minus theta over tau, and then you have this tau to the n as well. And then here we saw it for 2 tanks it's a 1, and then for 3 tanks it's a 2. You can show generally it's n minus 1 factorial here. So that's the general solution to n tanks in series. And if we were to plot this out, right, remember we know for 1 tank we've got a simple exponential decay. So 1 tank looks like this, and then if you plot out for 2 tanks, which is so this is n equals 1, then if you've got 2 tanks, it looks like this. So this is n equals 2, and then 3 tanks looks like this, n equals 3, and then 4, and actually as you go 5, 6, 7, you start to get this. You start to get a long 0 here, get a sharp peak there, not perfect 0, this is a number close to 0. Then you get a peak up here, and so this is n tending to infinity. So this is your tau here eventually. So does this look familiar? Right, as n goes to infinity, we seem to be getting something close to 0, and then a peak here, and then 0 thereafter. So of course it starts to look like a PFR at some point. And so that's because if you think of your reactor, you have the one mixed zone, so that's that. But as you add more mixed zones, and as you keep increasing the number of mixed zones, it starts to function as little plugs of fluid, right? So you start to approximate a plug flow reactor as n tends to infinity. So that's a surprising result, right? By taking the simple idea of perfect mixing and by increasing the number of mixed zones, we are in effect becoming a plug flow reactor. And this is something we didn't necessarily expect, because when we introduced this whole concept, we said that this was the perfectly mixed case and this was the perfectly not mixed case. But it turns out by taking these things in series, we start to approximate the perfectly not mixed case. And this is the first, perhaps, example where we are taking 2 idealizations, right? We said these are 2 perfect situations, perfectly mixed, perfectly not mixed. Neither of these are easy to replicate in reality, right? It's hard to get perfect mixing or perfect not mixing in the real world. In the real world, it's some blend between the 2. And now we have a theory that allows us to approximate the real world. So if we take some real reactor, which we are mixing, but where we know there are delays because there's perhaps no slip on the wall, so it's slow there, and then we have good mixing there, but it's not infinitely fast. So the real world is somewhere between the perfectly mixed and the perfectly not mixed case. And simply by adjusting our value of n, we start to approximate this real world case. So we can regard the tanks in series model as a kind of generalization of this whole concept of mixing. Okay, so that's what we can get from the perspective of the CSTR. Try to think of a way to start from the opposite side. Right, we've started from a CSTR, we've added them in series, and then we got to the PFR. How about from the PFR side? Is there any way for us to start from there and to move towards the CSTR-like behavior? Well, to do that, start thinking about the fact that we allow no lateral mixing in this case. Right? It's not the case that we can just try and put PFRs in series and then get a CSTR. We've already looked at that. We put PFRs in series, and we just got a bigger PFR, right? So the same approach is not going to work here. What we want to try to do instead is introduce a concept of dispersion, and it's closely related to the concept of diffusion. So in diffusion, even as a plug of fluid is flowing along, the molecules in that plug of fluid are diffusing. So if you introduce diffusion or more generally dispersion on top of convection, is there some way we can get to CSTR-like behavior? So I'll let you think about that. And for now, so we'll cover that topic in the next lecture. For now, I'd like to look at another type of real reactor case, and that's the laminar flow reactor. So in laminar flow, of course, we have our fluid which exhibits this parabolic velocity profile. And if we think of this, there's no infinitely fast fluid anywhere here. Right, there's zero slip at the wall, no slip at the wall, so there's zero velocity there. And then we have a maximum velocity here at the center line, so this is as far away from the wall as you can get. So that's the fastest possible fluid flow. But still, it's not infinite, right? There exists some finite maximum velocity that we define at the center line. So none of this fluid is exiting immediately from this reactor, but we've got these different velocities, and so fluid from each radial position is going to exit at different periods of time. So if we were sitting out here waiting for the pulse, right? So we pulse some tracer in here, and we watch what happens at the exit. We will first see a contribution from the center line. And it's going to take a finite period of time, so the distance of this tube divided by the center line velocity, that's how long it will take to exit here. And then after that first bit of fluid has exited, we'll start to get contributions from the slower fluid. Right, so we'll get some contribution from this shell, and then after that's exited, we'll get some from here, and so on. And of course, it does go on forever because near the wall there's still no slip. Right, so that's what's happening in the laminar flow reactor. That's what we expect to see. And the way that we find the RTD from this more complex situation is, first of all, we start defining the velocity in terms of the age. So once more, we start with the laminar flow definition, right? So laminar flow, we know that this is the laminar flow velocity distribution. So the distance from the center here, and then the maximum velocity, the center line velocity is there, where the center line velocity is twice the mean velocity. So there exists some mean velocity here, somewhere like that. And then that mean velocity we can estimate as the volumetric flow rate divided by the cross-sectional area. So that's our velocity distribution. And then we can use that to find our age as a function of radial position. So like we said, we will get contributions at the exit point if we divide the distance by the velocity itself. So the time taken to exit from fluid at radial position r, so here we are assuming that fluid is staying at the same radial position. It's not like one sort of sheet of fluid is at this radial position, and then as it flows it moves up here, and then another thing moves down there, right? It's laminar flow. It stays where it is in terms of its radial position. It's moving in Z, but it's staying at its radial position. So so fluid moving at position r will take L divided by the velocity at r, time units to exit. And we've just worked out u as a function of r. So we can write L divided by this thing. So we move the pi r squared up here, divide by 2q, right, 2q, and then divide by this thing. So 1 over 1 minus r of r squared. So it's just L over ur, right? So that's theta. And then if you look at this, you can recognize that you've got the volume of the tube here. So pi r squared L is the volume of the tube, right? And that's kind of lucky, because here the L was up here, and then when you divided by u of r, you got the pi r squared appearing here. And so we've just noticed up here we've got the volume of the tube. So it's the volume divided by the volumetric flow rate, so that's the space-time, and then the denominator stays as is. Right, so that's age as a function of radial position in terms of space-time. And now if you differentiate this, and of course there's no reason to do that, but we'll see it's convenient to do this. So if you differentiate this with respect to r, right, you've got r just down here, so you use the usual rule for differentiation and you get this. And then if you look at this expression, you can see that you can split off tau over 2 1 minus that, right, which is the same as that. You can split that off and that, and so you can rewrite this differential as theta squared times 4 over tau r squared r in dr. Right, so that's a useful thing to have. And the reason we are doing this is because we want to know what fraction of the fluid is spending a particular period of time there. So just to explain that a bit more, we can take our tube like so, and here, if that's the center line, we can choose a certain radial position. So let's say that's r, and then we can question for ourselves at this radial position, and of course that goes around like so. So we've got flow through this set of radial positions, right? So between r and r plus delta r, there are these flows, and so there's a certain flow rate that will come through r and r plus dr, and we can estimate this flow rate. So we can call that dq. dq is the flow between r and r plus dr, and so we can look for dq divided by q, right? This is the total flow. This is the fraction of the flow between those radial positions. So this is the fraction of the fluid in that radial position, and because we know radial position equates to space-time, it's also the fraction of the fluid in that age. So there's a particular age that applies to fluid at these radial positions. So this is the fraction of the fluid of those ages. So that's a fraction there, and then just replacing the stuff up here, right? We can rewrite it, and you can grind through the algebra here, and it comes out to that expression. And so this is the fraction of fluid elements in that particular age range. And so if you put this all together, you can say the age distribution at the exit is 0 up to tau over 2, and then after tau over 2 it's tau squared over 2 theta cubed, which looks a bit like this. So here's tau over 2. You get no contribution until tau over 2, and then at this point you get a contribution like that. So this is not an exponential decay. It is tau squared, which is a constant, over the variable theta cubed. So this is the inverse cube of theta. Theta is the variable here, of course. So that's E of theta for the laminar flow reactor. Okay, that's it for today. See you on Friday.